Hello everyone, welcome to my channel. In today's video, I'll walk you through the calculation of the design of a single reinforced concrete beam. This is problem number 2. The problem is a simple supported beam with a span of 25 feet is subjected to a uniformly distributed dead load of 2 kPa per foot and a live load of 0.5 kPa per foot, along with a concentrated dead load of 2.5 kPa and a live load of 1.25 kPa applied at the center of the span, which is this one here. The size of the beam is 16 inches by 26 inches and is given also the yield strength of steel, which is 60 KSI. The strength of concrete is 40 KSI. So we are required to determine the maximum factor design moment, the area of the required longitudinal tension reinforcement here, and also the tensile strength of the longitudinal tension reinforcement. So we will calculate that later to confirm that our steel tension reinforcement is yield. So continuing on, load determination. First, we have to write all the loadings in here. We have the uniform load of 2 kPa per foot, dead load, uniform load of live load 0.5 kPa per foot, concentrated load of 2.5 kPa, concentrated load of 1.25 kPa, live load, and the span of our beam is 25 feet. So here, this is our free body diagram of the beam. We have a loading uniformly load, and we have the concentrated load at the center. So since the moment of this beam is coincide at the center, the maximum moment, so we can just add all this beam formula. We have the simply uniformly loading. Formula is WL squared over 8. We have the concentrated load formula for moment, PL over 4. So we'll calculate first the uniform live load, uniform factored load. So we have 1.2 times the dead load, 2.0 plus 1.6 the live load, 0.5. Then we'll get 3.2 kPa per foot. Then the moment of uniformly distributed load for simple beam is WL squared over 8, this one, if we have this load arrangement. Then substitute all those value, 3.2 times 25 square all over 8, so we'll get 250 kPa per foot. So the factored load due to the concentrated load, we have PU 1.2 by 2.5, that is the dead load, and 1.6 times 1.25 live load. Then we will get 5 kPa. So this one here in blue. So the moment of concentrated load is PL over 4. Substituting all this value here, 5 times 25 all over 4. Then we will get 31.25 kPa per foot. So the total factored moment, maximum moment of the beam is the summation of these two here. WL squared over 8 plus PL over 4. Then substituting all those values above, 250 plus 31. Then we will get 281.25 kPa per foot. We will multiply this by 12 to be consistent with our design factored moment, so 3375 kPa. So by the way guys, if you forgot all this formula, there is another way of calculating this moment, because if you notice our beam is symmetrical, loading is symmetrical, so what you're gonna do is just to calculate sum up all the loadings, then divide by 2, and you will get the reaction of the support, edge of the support. You don't need to draw the moment diagram, summation of moment along Y, something like that, because it's very lengthy. That is only if the loading are symmetrical, similar to this what we have. So if you encounter that problem maybe in the board exam, because the time factor is very, is very important, so you can calculate something like this, direct calculation. If you have this, if you determine the R, and you have the sum up the moment at the center, you will get the moment 28.25, the same what we have here, times 12. Then you will get the same moment. That is a direct, calculation determining. That is if we have that similar loading like this. But if the load PU is off-centered from the center, you cannot use this kind of system. You need to draw the shear and moment diagram to determine the location of maximum moment. Okay, we have determined the factor design moment. So the next thing is we have to design the beam. So I listed all the formulas that we need for the design of beam here, the right side. And this formula is just straightforward actually. You don't need to memorize all this formula, because what you're gonna do is just to familiarize this diagram, stress block diagram, and we have the strain diagram. Then you will come up all this formula. And if you substitute all this A from here, from value of A to this one, you will come up the quadratic equation. So you don't need to deal with the quadratic equation. So what you're gonna do is just to use this simplified formula to get the steel ratio. So now we will calculate the steel ratio of the steel, assuming that the tension, the steel yield. So we will assume that the tension control, so that we can use the yield strength of steel Fy, and Phi is 0.90. So now we will calculate the value of M, calculate the value of Rn, so that we can substitute it here. Then we can, we will get the value of the steel ratio. So 60 divided by 0.85 times 4, which is the strength of concrete, and this is the strength of steel. So we will get 17.65. For Rn, we have moment. We already have calculated the moment, which is 33.75 all over 0.9 times 16 times 26 squared. Then we will get 0.347, the value of Rn. So direct substitution to this equation, we will come up to this calculation, 1 divided by M, which is 1765, close parenthesis 1, minus the square root of close parenthesis 1 minus 2 times M, 1765 times 0.347 Rn, then divide by F sub y. F sub y here is 60 KSI, not 60,000, because the unit of our moment here is in kips ins, so we need to be consistent with that here. So kip ins, Rn kip ins, so this should be kips also. So the value of steel ratio is 0.0061. The required steel is rho BD. The steel ratio times the width of the beam and times the depth of the beam. So the required steel ratio tensile reinforcement is 2.54 square inch. Now, since we already we have determined already the required steel reinforcement, we can now then proceed to determine the value of A, so that we can get the value of C. C here, we need the C to determine the C, so that we can determine the tensile strength of steel, whether it is yield or not. So the value of A is 2.54, which is this one, times 60, divided by 0.85 times 4, strength of concrete times the width B is 1. So we got 2.8 inches. So after determining value of A, we will determine the value of C, because C is simply A over beta. So beta here actually is controlled by the strength of concrete. It depends on the strength of concrete. So beta is 0.85 for the strength of concrete less than or equal to 4 KSI as per the ACI code. So 2.8 divided by 0.85 is equal to 3.29 inches. So now we have already determined the value of C. By ratio and proportion, we have C is to 0.003, then the depth of here, the tensile strength, D minus C is to 3.29, which is value of C. So it's equal to 0.0207. That is the actual tensile strain value, which is greater than 0.005. So which means our reinforcement is yield tension control. So our assumption is correct. So guys, if you found this video helpful, please don't forget to like and subscribe. And thank you for watching. I'll see you next time. Bye bye.